Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. So, in this video I want to talk to you about a charging circuit for accumulators, basically the second version. I will have to deliver a lot of informations in one video. So please bear with me as I will literally jump from one thing to another. I will try to give all the informations as easily as possible and in a logic order as possible. So a while ago I made a video called BMS with discrete components version 1, where I basically attempted to create a circuit that acts both as a protection circuit for an accumulator, especially a Litiu accumulator, and as well as a charging circuit for that same accumulator. The design was not bad, but it had some shortcomings, and all in all I decided to study this problem a little bit more and basically come with an improved version. Meanwhile, I also realized that these are two completely different circuits that don't make much sense to be placed in the exact same board, in the exact same place. So I decided to split things up a bit, and basically I've created a second version, which is something that I would like to show to you. There are basically two circuits, because I split apart the charging controller and the battery protection, the accumulator protection circuit. So this is what I would like to show you, and also a little bit of some of my practical exercises, practical chargings of one particular accumulator. So let's start talking a little bit about the general idea, and then we will dive deeper into the details. So I realized that when it comes to, Litiu accumulators or lead accumulators, it doesn't matter if it's lithium-ion, lithium polymer, or lithium whatever. Also doesn't matter if it's the so-called sealed lead acid battery or any other kind of lead acid battery. We basically need to have more or less these three elements. A charger, which is a device that handles the charging of that particular accumulator. A cell balancer, which is optional, and at least when we have multiple lithium cells in our battery, in our accumulator, we would want to have such a thing to make sure that all cells remain in a certain balance, and an undervoltage protection so that the power will be cut, the power going from our battery, from our accumulator to our load, whatever the load is, will be cut if the battery's voltage will drop under a certain level. Now this is more this is needed both in lithium batteries, also in lead batteries. The cell balancer, on the other hand, is a thing that is needed more in lithium batteries, lithium accumulators, not so much in lead accumulators. Okay, so I will keep saying accumulators because this is the word that we actually use in my language. In English I see that you keep using the word battery, even though it's technically speaking not a battery. Yes, it's a rechargeable battery, but anyway, I find the word accumulator to be a lot clearer and easier for me as a non-English speaker. So I will keep using this word. Replace it in your mind with the word battery if you are used to the word battery. For us, batteries are only the ones that cannot be recharged. You use them and then you throw it away to the trash. Anyhow, I am yet to study the workings of cell balancers in order to be able to come with one, even a rudimentary one. So I have not yet created any, but I have improved the undervoltage protection circuit from version 1, and I have also created a separate charger because like I said, I realized that the charging circuitry doesn't make sense to stay inside the mobile device that has that particular accumulator. It can be and it should be on the outside, okay? In order to, you know, spare space and other considerations. So this is what I will be showing you in a moment. Meanwhile, please allow me to thank the sponsor of this video, which is PCBWay. They are a leading PCB manufacturer with many capabilities to help you build PCBs, assemble them with components if you want to, help you create plastic cases or even metal cases if you wish to do so. You can easily get an instant code for PCB manufacturing from the website's front page, upload the Gerber files and have your PCBs created in just 24 hours. If you need to get more for your project finished, they also offer PCB assembly services with manufacturer direct pricing, so you can have your PCBs delivered with components soldered on. This way you don't have to do the tedious work yourself. Or perhaps if you want just the cement stencils so you can solder the components yourself, they can also help you with that. Just have to finish your design in your favorite design software, upload all the necessary files to PCBWay, and you'll be contacted by one of their professional representatives after they manually review your project, offering you one-on-one customer service to make sure that your circuits get fabricated just the way you want. If you're building a circuit for a device that will need a case in the end, they can help you with that as well, offering you 3D printing or injection molding services to have your custom-made plastic case, or perhaps CNC machining services to help you with a custom metal case. All you need to do is go to PCBWay.com, the link is in the description. Thank you very much PCBWay for sponsoring this video, and now let's get started with the circuit. Or I should say circuits, because there are two of them. So let's start with the smallest one because we can quickly explain it. The undervoltage protection. Now in the previous version this was done by just a Darlington pair, a few resistors and a P-channel MOSFET, which is not bad, but it has a bit of a bouncy way of working, and I wanted to add some form of hysteresis to this. So what I ended up using is a circuit that has the same P-channel MOSFET, but has 3 NPN transistors, no longer in a Darlington pair, but rather in a different configuration. The first 2 transistors with the associated resistors, Ru1, Ru2 and Ru13, are a simplified form of Schmitt trigger. Okay, well, the so-called Schmitt trigger with 2 bipolar transistors. Officially it uses 5 resistors, but you can just use 2 of them and it will be good enough. With these values of resistors that I basically tried and tested practically on a breadboard, they're not just theoretically calculated, they're actually tested on a breadboard. They cut off power from the output when the input voltage drops below 3 volts, but they don't allow power back up until some 3.4-ish, 3.5 volts or so. The idea is that these 2 first transistors, T1 and T2, They have their emitters connected together. Their emitters are connected to the ground through the same resistor, which is 3.3K in this particular case. However, their collectors are connected to separate resistors. So this makes it so that when each transistor is turned on, and it's turned on to the maximum, it's taken to saturation, R13 will form a different voltage divider based on whether it gets connected to R1 or to R2. And therefore we have two different voltage thresholds, which makes T1 transistor turn off at a certain threshold but turn back on at a different threshold. And really this is the only significant modification that I've done to the circuit. So this is the circuit that will need to be having the battery, the accumulator on the input, and then on the output whatever else we want to power from that accumulator. This can be built in a semi-dev version, and it will occupy a very small space, so that it can be used basically in any mobile device that we might want to create and be powered from an accumulator that needs to be protected. Okay, so there's not much engineering going on. Let's move to the charging circuit. So like I said, the charging process, in my opinion, right now, after studying these things for the last few weeks, the entire charging process doesn't make sense to happen inside the mobile device that has the accumulator. It makes sense to happen externally. So it makes sense for us to have an external device that handles the charging process. Now, I wanted to create a charger that is absolutely universal. However, that's not possible simply because not all accumulators charge in the same way. They have different charging methods, so at least when it comes to Litiu and lead accumulators, they have the same method. So I was able to build, let's call it semi-universal charger for Litiu batteries and lead batteries, at least for 6 volts and 12 volts lead batteries. However, there are also nickel cadmium and nickel metal hydride. Those kinds of accumulators need a different kind of charging process that monitors the temperature as well. So for those accumulators I will need to study and build a completely different kind of charging device. Okay, so we will have to settle for only Litiu and lead batteries. Now, I have studied this problem from the internet. Sadly, informations are a bit scattered and they're not so well documented in a central place. Anyhow, from what I was able to tell, both Litiu and lead batteries need to be charged in a two-step process. Technically speaking, some designs actually use 3 steps or even 4 steps, but really 2 steps are more important, and the whole thing can be resumed to only can be simplified to only 2 steps. The first step is to inject a constant current into the accumulator that we wish to charge and monitor the accumulator's voltage. And then when the voltage has reached a certain maximum level that is dictated by the type of accumulator that we are using, then we have to stop pushing a constant current into that accumulator and switch to constant voltage, but still monitor the current. The charging current will go down, down, down up until it will become very, very small, and at a certain threshold we can just stop the whole charging process and consider that accumulator to be completely charged. So basically we have two steps. The first step is constant current mode, the second step is constant voltage mode. Okay, the only difference between these kinds of accumulators are in how big this current has to be or can be, and what is the maximum voltage that the accumulator must reach. And also, what is the threshold for the lower limit below which we can just cut the entire charging process and consider it done. From what I've seen, there are two types of Litiu batteries, at least from a perspective of the maximum voltage that is inside. Okay, we have 4.2 volts Litiu batteries, which are lithium-ion, lithium polymer, lithium iron phosphate, the usual kind of accumulators that are everywhere on the market right now, and that form, I don't know, more than 90% of the market. These have a nominal voltage of 3.7 volts, but at 3.7 volts they are considered to be around 50 to 60% charged. The maximum voltage up until they need and they can be charged is 4.2 volts. Now, lately I have seen that on the market there have appeared here and there, not very often, not in many places, but there have appeared the so-called Litiu high voltage kind of accumulators, which, like the name implies, they are able to be charged up to a higher threshold, up to a higher voltage. And I found that to be 4.35 volts, where it is considered to be 100%. And the nominal voltage is around 3.8, sorry. So instead of 3.7 at a regular Litiu battery, Litiu accumulator, these high voltage Litiu accumulators have a nominal 3.8 volts and a maximum of 4.35. Okay. As far as lead acid batteries are concerned, they come in many configurations, at least when it comes to the number of cells that they have inside. However, we will always treat them as a single cell accumulator, because unlike Litiu accumulators that are actually built from multiple cells where we actually have electrical access to each cell, when it comes to lead batteries, lead acid accumulators, we don't have electrical access to each cell, and quite frankly we don't care, we don't need to. We have access only to the entire accumulator. Okay, so then we can have 6 volt accumulators, 12 volts accumulators, 24 volts, 48 volts, and so on. Now, in order to work with 24 volts or more, I would have needed to, well, design my my charging device in a bit of a different way, and I honestly did not saw the point. From what I've seen, at least when it comes to small capacity accumulators, the 6 volts and the 12 volts are the most widespread ones on the market, right? And so I made a charger that charges lead acid batteries for only 6 and 12 volts. I didn't care about others. Okay, good. Now, when it comes to these kinds of lead accumulators, well, they can also be split into two different categories. The ones that are called flooded. Okay, this word means flooded. In actually, I can temporarily change it. So there are the so-called flooded lead acid batteries and the so-called sealed lead acid batteries, aka VRLA, aka AGM, aka gel. Okay, AGM stands for absorbing glass mat or something like that. Gel is just the word gel because the electrolyte is trapped inside the gel. Anyway, in these so-called sealed lead acid batteries, the acid is trapped it cannot escape. So there are some benefits that those accumulators have. I'm not going to start listing them because it's beyond the point of this video. The point is we need to distinguish between flooded batteries, accumulators, and sealed lead acid accumulators, because their voltage is a little bit different. So we can charge the sealed ones a little bit more than we can charge the flooded ones. Okay, so I wanted to create a charging device for these kinds of accumulators. In essence, what we need to create, since we need to have constant current and constant voltage, what we need to create is nothing more than a power supply that has both constant current and constant voltage mode that is a bit more fancy in terms of how it is able to work and how we are able to work. Okay, it needs to have just a few extra features that the usual lab power supply doesn't have. So because I set my mind to essentially design my own, I also wanted to be as easily usable as possible. So the front panel looks like this. I just wanted to have a switch, and I will show you in a moment. I will show you an actual video of the front panel and the rest of the device, as I will talk to you a bit more about the aspects. I wanted just to have a switch with which to basically tell the charger what kind of accumulator am I trying to charge. I needed to have a double switch because I needed to basically control both the maximum voltage and the cutoff current. So on the market there are rotary switches with 2 × 6 positions. So basically you have 2 switches into one. Each switch can have up to 6 positions, which is perfect because I have 2 positions for Litiu and 4 positions for lead. Okay. I also wanted to have a potentiometer that is able to it allows me to set the amp hour rating of my accumulator, which can be easily read from the accumulator's label. Because I did not want it to actually have to calculate the currents that need to flow into the accumulator. I just wanted to set the amp hour rating of the accumulator himself, and this device to basically do the rest. And also I wanted to have a little bit of extra flexibility in terms of how slow or how fast my my charging process is done. So I wanted to essentially be able to adjust the constant current that we are feeding into the accumulator in the first phase. Okay, so I have an extra potentiometer here, which is the C rating from 0.1 to 1. Okay, we cannot have more than one. I mean, yeah, theoretically we could have more than one, but it doesn't make sense. From what I have read on the internet, for lithium batteries it is recommended to be anywhere between 0.5 and 1 C rating. For lead acid batteries, between 0.1 and 0.3. In other words, a much smaller current needs to be used. Okay. Now the C rating is in direct correlation with the amp hours of the lead acid or of the battery, of the accumulator, right? So if we set, let's say, if you have a 1 amp hour accumulator and we set the C rating to 1, then we will be charging that accumulator with 1 amp. If we set it to 0.5 C, then it will be it will be half an amp that will be thrown towards the accumulator in the first phase of constant current mode. Okay, if we set the amp hour to 3, let's say, and the C rating to 0.5, then we will have 0.5 multiplied by 3, that is 1.5 amps of current flowing into the accumulator in the first phase. Okay, and I also wanted to have a couple of LEDs that turn on when the process is finished. One when the accumulator has reached the maximum voltage, and another one when the process is fully finished, completely finished. Okay, and this is pretty much what I have on the front panel. Anyway, I will be talking a little bit more, and I will be showing you a little bit more a bit later. Now let's dive into the schematic, which looks like this. I know it might look scary at first, but trust me, it's actually simple. It's actually easy, and I will explain it to you in a moment. Okay, in order to explain this to you, I will make use of this diagram on which I have placed several colors, because it is easier for you to see different blocks and to understand each of them what they are doing. Okay, so almost half of this device, by the way, I forgot to mention, this device, this charging device, is technically speaking just a controller. It needs to, I mean, he needs to receive power from something else. So you need to, on the inputs, you need to supply anywhere between 10 and 20 volts, depending on what kind of accumulator you wish to charge. And of course, that power supply needs to be able to give at least the current that you are trying to push into the accumulator, preferably even more. Okay, so it's not a completely standalone one. Okay, it's not difficult, on the other hand, to just buy a transformer, a rectifying bridge, and some filtering capacitors and put those on the input. You can definitely do that. And of course, what is also worth mentioning is that the entire circuit is very flexible. It could be adapted to work with any other kind of accumulator, any other kind of situation. Okay, so on the first half of the circuit, all we have, it looks big, but it's not. It's just because we have quite a lot of resistors in series and a couple of switches that take up quite a lot of space on the actual sheet. And we have a voltage source. Essentially, we have a standard voltage source, a constant voltage source that is able to provide us with several other voltages that we need in order to control the rest of the circuit. Okay, because the entire device is controlled through different voltages, so we need to be able to generate those voltages. We need a voltage for each type of accumulator that we are trying to charge, because like I have shown you in this table, right, we need to be able to monitor the maximum voltage, but the maximum voltage is a function of the type of accumulator. So this is why we have a 6 position switch with many resistors placed across a 7.5 volt Zener diode, which is powered, let me show you a bit clearer here, which is powered from a constant current source. Okay, I have chosen PSSAE to 2021 integrated circuit, but that's just because I had one lying around. You can use any constant current source here, any integrated circuit, or just create one with discrete components. I will show you in a moment the fact that this integrated circuit is nothing else than just you know, a bunch of components placed together, just one transistor, 2 diodes, and 2 resistors placed together inside this IC. So it's a very simple IC that can be very easily you know, created with discrete components. I used one just because I had one ready. So I used such an IC plus a 68 ohm external resistor to set the proper current for this Zener diode in order for the Zener diode to give me 7.5 volts. And I have used this 7.5 volts to divide it down to several voltages. Now, in order to work with up to 12 volts or beyond, it wouldn't be impossible, but it would be impractical. So what I'm created is literally half the voltage of these maximum ratings that you see in this table. So basically I halved each of these voltages, and I've created a standard voltage out of every one of them with these resistor dividers, and this half a voltage will be later compared with half the output voltage of the entire device. So instead of comparing the full voltage, we are comparing half of them. Okay. You will need to handpick these resistors, and you will probably need to do a bit of calculations. In some cases I needed to use two in series in order to get a higher value. In other cases I placed two in parallel, just because they were easier to obtain. They were easier to create that particular custom value that I needed to have here in order to have the correct voltage drop, okay, in order for me to have the correct 6 levels of voltage. And that's really all we have in the first half of the circuit. We also need to generate a couple of more voltages in order to control the constant current that we are injecting into the accumulator, and also to detect the threshold current limit. So for that I have also taken this 7.5 volts voltage from the Zener diode and sent it through a 1K potentiometer, and then from the middle point, from the cursor of this potentiometer, I have chosen to connect a second potentiometer, which is 100K, 2 orders of magnitude more. This is so that it will not interfere with the value of the first potentiometer, and a couple more resistors in series. The point of the first potentiometer is essentially to adjust the accumulator capacity in amp hours. Okay, it's this potentiometer on the right that can go up to 7.5 amp hour. Why? Because I have 1 volt per amp convention, and I have 7.5 volts from my Zener diode, so I can only adjust this up to 7.5 amp hour accumulators. Not a problem. Even if we have higher accumulators that we want to charge, we simply turn this up to the maximum and it will charge a little bit slower, but it won't be a problem. And then I needed to have another voltage that represents the C rating. Okay, so whatever the first potentiometer is set to, the C rating is always from 0 to 1. So this is why the second potentiometer comes connected to the ground from the first potentiometer's cursor point, right? And I wanted the second potentiometer to be able to give me voltages equivalent for currents from 0.1 C up to 1 C, not lower than 0.1 C, because then it will create some problems with the lead batteries. Well, with all accumulators actually it would create problems, because we need to use 0.1 C and 0.01 C as the lower threshold to detect when the charging process is finished. So I use this 100K ish potentiometer in series with the 12K and the 1.3K. Okay, the 1.3K gives us 0.01 C rating, and 12K potentiometer resistor gives us the 0.1 C level. Okay, and of course these voltages need to be connected in the correct pins of the second switch, with rotary switch, or should I say the second segment of the rotary switch, in accordance with how we are connecting the first segment to the other voltages. Okay, so this is how we control the rest of the circuit. Now let me get back to this color version. I have explained basically the pinkish left side. Now what we have in the rest of the half of the circuit is basically with green a bunch of transistors, a power transistor BD911 and a smaller power transistor. These form a Darlington pair. These are basically a switch. They act like a switch that takes power from the input and throws it out on the output towards the accumulator that we are trying to charge. And we will use this switch to basically close him and open him enough so that we have the correct voltage on the output and the correct current. Okay, pretty standard for any linear power supply. I also have an extra transistor here with an extra shunt resistor, 0.15 ohms, placed across base emitter junction of this extra transistor. This essentially makes sure that no more than 3 amps flow through here. If more than 3 amps try to flow, then this transistor will open. Well, actually, the protection starts at about 4 amps in reality, which is good enough. When more than 4 amps try to flow, they will generate enough voltage on this shunt resistor to open this T4 transistor to basically make the base of the Darlington pair fall below the point in which these transistors can still remain open enough to pass a larger current. So this is how the extra current protection is made, because we can never rely completely on the rest of the circuit. Okay, we have two op amps here, one to the left, one to the right. These are actually comparators. So I actually used LM339, which is a quad comparator, the cheapest one on the market. It does its job pretty well. It's an open collector comparator, meaning the outputs of each comparator can either be left at very high impedance or pulled down towards the ground. When they will be pulled down towards the ground, this power stage will be shut down. When the outputs will be set to high impedance, this power stage will turn on again and allow current to flow back. What else is there? This left side comparator basically controls the output current, okay, and sets the entire circuit into constant current mode, because on the positive input we have this voltage that comes from the potentiometer with which we set the C rating, and on the negative input we have a voltage that's equivalent to 1 volt per amp of the current that is flowing towards the outside. This voltage comes from a different circuit. I will talk a bit in a moment. Okay, so this left side comparator basically compares these two levels and shuts down the power stage when the current has gone above that threshold. The right side comparator monitors the output voltage. As we can see, we have two resistors here, Ru11, Ru17. Both have both are 12K. Okay, let me show you a clearer image. Both are 12K. It doesn't matter. I've chosen 12K because it was in handy. They need to have the exact same value, and they preferably need to be hand-picked to have the exact same value. They halve the output voltage and they feed it to the negative input of this other op amp, and the positive input receives standard voltage, reference voltage from the first switch that we have here, from which we are basically telling this entire device what kind of accumulators we have on the output. So this second comparator basically will get triggered and will shut down the power stage when the output voltage has gone above that threshold. And because that's the end of the, technically speaking, that's the end of the first stage, the stage in which we inject a constant current and we are monitoring the output voltage, I decided that I would like to basically see the fact that I am at the end of this process by turning on a red LED. And this is why the output is not connected straight to the base of the Darlington pair. It's connected through a red LED. Even though the red LED will obviously have a certain voltage drop, it will not be a problem. Okay, for the output voltage will still be able to drop down to 1 volt, which is more than enough, because on the output we see that we have 2 diodes. They don't have to be 2, they don't have to be Schottky diodes. It needs to be one diode that can, a rectifying diode or a Schottky diode, it doesn't really matter, that can resist to a current that's more than the current that we are trying to push towards the accumulator that we're trying to charge. I did not have any power diode at hand, so the only ones that I had were 1N5822s, which are Schottky diodes up to 3 amps. I decided to put 2 in parallel because I want to be able to work up to 3 amps, and yeah, it would be dangerous to allow just one diode to handle 3 amps, maybe even more continuously, so I decided to put 2 of them. This makes sure that when the device shuts down, there will be no significant current flowing backwards from our accumulator into our device. Okay, the only current that will flow will be a very small one down through these voltage dividers. Okay, but 24K is really not a problem. It will generate just a few microamps of current from our accumulator. Anyhow, yeah, from our accumulator that's connected to the output. Okay, so I have explained how the constant current and the constant voltage mode work. Now, of course, in order to monitor the current, we need to have a voltage relative to the ground that is proportional to the current flowing towards the output, towards our accumulator, okay? And for that, we need to use another circuit that creates this translation, this transformation between the current and ground referenced voltage, preferably high enough so that we can work easily. And this is what we have in purple. Here we have another comparator or an op-amp. For this device we can use either op-amps or comparators. They don't matter all that much. I've used a comparator because it was just in handy, and I wanted to work with a comparator on a project and see how that goes. Anyhow, this circuit that I've selected in that I've marked in purple handles the conversion between the current and a ground referenced voltage that needs to be 1 volt per amp in order for us to, you know, work easily. And I'm not gonna go in this video in great details about how this works. If you want to know how I managed to come up with this circuit, you can just post a comment and I will make another video dedicated to this and the other circuit that I actually found on the internet that I've tested, and why I needed to use this and not that one. What I will explain to you very quickly is that we are using this 0.1 ohm resistor, this shunt resistor, that is in the path of the high current. Okay, there's a high current flowing through here from our input towards our accumulator on the output. Based on the current that flows, okay, we will have obviously a voltage that will be formed across this shunt resistor like this. Okay, so we'll have plus in the left, minus in the right. In order for us to create ground referenced voltage, we are performing some tricks to essentially create, to mirror this voltage here on this other resistor, which I have chosen to be 100 ohms. And on this resistor we will have exactly the same voltage that we have on this shunt resistor, okay? Relative to the ground. The resistor himself goes underneath the image, okay? The ground is not this line here that goes to the minus input of the op-amp. The ground is actually further down below, as you can see here better, okay? This is just a zoomed version so that I can better, you know, draw the explanations. Now, this resistor has 100 ohms because we want to have a certain current flowing through him when we will have this voltage that will mirror this other voltage, and we want that current to be both high enough, small enough for us to work with him, but high enough to potentially allow us to generate a higher voltage through another trick. Okay, so I have chosen 100 ohms, and actually I haven't chosen per se, I have just taken these values from a data sheet. Again, I will make a different video if you are interested about this. The idea is that if we have 1 amp of current flowing through this 100 milliohm resistor, shunt resistor, then we have obviously 100 millivolts across him. When we make it so that we have 100 millivolts here, 100 millivolts divided by 100 ohms means that we will have a current flowing through here, through this resistor, that will be 1 milliamp. Okay, I'm not drawing very well with the mouse, but anyway, you understand. So, in order to have 1 volt per amp, all we need to do is have this current flow through more than 100 ohms. How much more? Well, 1 kilo ohm. Okay, if we have 1 milliamp of current flowing through 1 kilo ohm, then we will have 1 volt. And so we place this 100 ohm resistor in series with this 900 ohm resistor, which is not a standard value. I actually used 2 resistors in series in my circuit, and here basically we have 1 kilo ohm through which flows 1 milliamp for every amp of current that flows in the outer loop. So here we will have, you know, 1 volt per amp. And this is the voltage that is proportional to the current and that can go in the rest of the circuit and act as a, you know, as a reference, sort of, as a measurement current, a measurement voltage. Anyhow, I'm gonna leave out, you know, the rest of the resistors. Why are they like this? What's up with this capacitor? I will briefly mention that this capacitor C2 here, which I have determined experimentally to be 100 nanofarads, it's good enough. And this other capacitor C3, which needs to be 10 microfarads, that is connected in this point where the switching Darlington pair element meets the output of these 2 comparators. These 2 capacitors are needed for the so-called frequency compensation, because since I did not use op-amps but rather comparators, they needed this frequency compensation, otherwise they just started to oscillate and not give me nice you know, voltages and currents on the output. So this is why these two capacitors are here. And what I wanted to have more is a way to know when the entire charging process is finished, and basically a way to a way for this entire device to shut himself down, and in order to let me know that it is finished, to basically light up a diode, a LED. So this is why we have this fourth comparator here with two NPN transistors and some extra components. The one marked, so this entire area marked in blue, in light blue. Whenever the current going towards the accumulator falls below a certain threshold, this comparator will turn on, which in turn will turn on both of these transistors. One transistor, this T6, this T6 is used to drag down the minus input of this comparator and make it so that this comparator stays forever turned on. I mean, with the output set to 1 logic. This is basically like a sort of hysteresis, okay? So that the entire device remains shut down. And this second transistor with a green LED is connected to the same control point and essentially does the same thing. We'll drag this Darlington pair power element down to the ground, and we'll make it so that we will no longer have voltage on the output towards the accumulator. Okay, so we'll essentially shut down the entire charging device, and will let us know that the charging process has been finished. We need to have a pull-up resistor. Since all of these comparators have open collector output, we need to have pull-up resistors. Okay, so our R6 here, 39K, for this current measuring circuit, this is what it is. It's a pull-up resistor. This R20 of 12K is also a pull-up resistor that needs to be connected from the input positive point to the output of that comparator. In order for this comparator to not accidentally turn on quicker than he needs to by mistake, I have also placed a 0.5 microfarad capacitor here, C4, and of course we will want to reset this process when we have you know, charged an accumulator and we want to get to the next accumulator to charge him up. Well, we need to reset this entire circuit because like I said, this end of charging process circuit will latch this entire charging, will disable this entire charging and will latch. So we have push to make, I don't know how do you call it in English. It's a switch that is normally open and it closes only when you press him, and when you release him it releases back and it turns into an open circuit again. Okay, that's pretty much it. We also have a resistor R23 here for 12K in the negative input of this comparator, so that you know, we don't interfere negatively with this 1 volt per amp reference voltage. And really, that's the entire this is the entire design. It's not complicated at all. It can also work as like, if we change things a little bit, this is basically a classical circuit of a lab power supply, if you think about it, you know. You only need these 3 comparators. You don't need this 4th one that latches into shutdown mode. and you have a constant voltage and a constant current control of this entire thing, and this can easily work as a lab power supply, you know, provided that instead of these switches and these standard voltages here, you just have a bunch of potentiometers. You can easily create a lab power supply out of this thing. So this is pretty much it when it comes to, you know, designing and building this thing. Let me quickly show to you how the end result is. I still need to work a little bit on the plastic case. It's not fully finished, but it doesn't matter. What I have now is the accumulator powered by a lab power supply, trying to, you know, charge this Litiu accumulator that I have recovered from a mobile phone that I did not use anymore, an old Nokia mobile phone. Okay, this diode is placed here just to act as a contact, because I don't have a socket good enough for this accumulator, so I needed to improvise something, you know. One thing that I definitely can tell you is that you will need to be careful about the way you connect your accumulators to this charging device, because every voltage drop matters. Okay, for instance, if you as you can see in this image, the red LED is turned on. When the red LED is turned on, it means that as far as the circuit is concerned, the maximum voltage has been reached already. However, if you take a look on this voltmeter that is placed directly across the accumulator, it only shows 4.089 volts. Now, needless to say, it is important to, you know, choose those long string of resistors wisely. I did. I definitely have a threshold close to 4.2 volts, but my device started to basically end the first cycle below 4.1. Why? Because I have more than 100 millivolts of voltage drop across all the cables that I used here. I used basically only crocodile cables. Apparently they don't make good enough connection. So I'm losing more than 100 millivolts on the cables themselves. Okay, this is why you see this discrepancy. I was looking here at the voltage that's respective to the current flowing towards the accumulator. You know, this is the board. It's not super great, but it's not bad either. It's made in the classical way of just using a board that does not have copper and just using the components, wires, to create the equivalent of copper traces, which works perfectly fine. Nothing fancy. I have a link in the description if you want to watch a video about that particular topic, alternative ways of creating circuits. The only PCB here is the small green rectangle on the left of the yellow board, which I needed to have it created professionally in order to use a small SMD component, which is that constant current source. But like I said, you have enough space to add just a couple of resistors, diodes, and one transistor to actually you create that with you know, with discrete components. And this is pretty much it. Now, I haven't had much time to charge and discharge several accumulators. I will do more testing. I have ordered a couple of so-called universal tablet Litiu accumulators. They haven't arrived yet. I also bought a few months ago some very small accumulators, like smaller than a normal battery. I will definitely do some more tests, but I need to create some special casings for those accumulators and solve this problem with the connections so that I don't lose more than 100 millivolts on the cables and you know, on the crocodile connections alone. So this is pretty much it. As far as I'm concerned, it's a very useful device to have in the house, especially when you're building things, when you're working with accumulators. The fact that it's semi-universal, you know, makes it very flexible, very versatile. I will come back in the future with circuits that are able to charge nickel accumulators. But like I said, I need to study some more and I need to work some more. I will put on Patreon project files for this device. You know, the schematic in PDF form. I will put the schematic of the board as well. And KiCad files, I would rely on KiCad files a lot more if I were you. I will also put the front panel. You just need to, you know, change some words here. I have a project in CVG format. You can open it in Inkscape. Anyway, I will put everything on Patreon in case someone wants to, you know, duplicate and just have this circuit at handy so that you don't have to redraw it by yourself. And yeah. So thanks a lot for watching this video. I hope you found it interesting. I hope you've learned something now. Please make sure to hit the like and subscribe button if you would like to see more. And I will see you next time in the next interesting video. Thank you very much. Bye bye.